In this lecture, we will study the prediction of the branch target. Let's start by considering what happens, considering the format of a branch instruction in RISC-V so that we can remind it of what needs to be done in order to compute the branch target when we are executing a branch instruction. So the branch instruction is a SCP type instruction in RISC-V. And what the branch does, and we're going to consider this example for a branch not equal. So if the two registers S3 and S4 do not contain the same value, the branch instruction will take the current value of the program counter and add the immediate value that's encoded in the branch instruction to it to be the new program counter. So this is the format for this instruction RISC-V. And let's recall how this branch target is computed. What we want is to jump to a label in this example that's 12 bytes away. So the first thing that we need to do is to consider what is the value 12 when we express it in 13-bit signed binaries. So this is the value 12 expressed in 13 bits, and we did this spacing so that's easier to read this value. So we space in 4-bit groups. And what we'll do now is to take this value and we'll extend this immediate to 32 bits. Next, what we need to do is to take the value of the program counter of the branch instruction that we are executing, and we need to add to this immediate value that has been signed extended, and that give us the new value of the program counter that we're going to use to execute, that will be the instruction that will be executed when the branch is taken. So let's also recall that this immediate value in RISC-V is stored in a shuffled way in the instructions. And the reason it's stored in this shuffle way is to make the implementation of the hardware that will access this immediate value faster. And remember that in RISC-V, the bit 0 is always 0 because I cannot jump to a branch that is at an odd address, even in a 16-bit RISC-V architecture. But the point of this recapping is for us to consider all the operations that needs to be done in the pipeline when I'm executing a branch that is taken. I need to take the current value of the PC. I need to take this immediate shuffle in the instructions do this shuffling, and I need to do this addition. All this takes time. So if I look at the pipeline, I'm going to be doing the branch prediction at the fetch stage. And if I predict this branch to be taken, I need the address of the target instruction for this branch. But the target will only be computed multiple pipelines, after multiple states in the pipeline. Therefore, predicting that a branch is taken, but not knowing the address of the target instruction is not going to be very useful. So the question is, could we predict the target sooner than it takes to compute it? And that is what this lecture is addressing. We're going to introduce a new structure in our hardware that is the branch target buffer. And it's called the BTB. So the branch target buffer is a full associative cache that has tags that are taken from the address of the branch instructions, and associated with each one of those tags, there is the target of the branch, that is the address of the instruction that will be executed when that branch is taken. So in this case, now that we have this cache-like structure, if the branch is predicted taken and there is a hit in the BTB, so we need to consider that the first time that we execute a branch, the target of that branch will not going to be stored in the BTB. I will have to compute that target, but once I compute the target, I can add that entry to the BTB, and now I will have a branch tag associated with the target of the branch in the BTB, and now I could have a hit. So in the case that I predict the branch taken and I have a hit in the BTB, I'll take that the address of the target of the branch from the BTP, and I'll immediately put it into the PC without having to compute it. That's the idea of the BTP. One of the questions in terms of design is, should we integrate the BTP and the PHT in our design? So let's look at what it will look like when I do this integration. So when I do this integration, it means that I'm going to take the tag from the branch address, and that tag will going to give me an access to not only the address of the target instruction, that is what the BTP usually contain, but also to the prediction bits that I'm going to use to make the prediction. So I'm integrating the BTP and the PHT. There are some consequences to this design. The BTP will need much more space than the PHT. And remember that the BTP is a full associative cache. So whenever I have an instruction hardware that's a full associative cache, the number of entries in that structure is limited because I need to search all the entries when I'm looking for the value, for example, of the target of a given branch. So the number of entries in the BTP is limited by these factors. And when I make this integration, the number of entries in the PHT will have to be the same number as the number of entries in the BTP. And of course, I must access the BTP in a single cycle as well. So that also limits the size of the BTP. So that's the main limitation of that design. So what we're going to do next is to consider a design where we decouple the BTP and the PHT. In this case, I'm considering a local bimodal predictor, right, where I only take some bits for the PC to index the PHT. And I take some bits of the PC to index the BTP. In these drawings that are taken from the textbook, they are kind of cartoonish drawings. Of course, if the size of the BTP is different than the size of the PHT, the number of bits used to index those structures will be different, not the way it is illustrated in this picture. But this cartoon here gives you the idea. So I'll take some bits of the PC to index the PHT and the BTP, and the other bits of the PC will become the tag of the branch that I enter into the BTP. So in this case, I can have a parallel access between the BTP and the PHT. And if the PHT says that the branch is taken and there is a hit in the BTP, then I can take the address from the BTP to put it into the PC. Some of the things to consider is that for space efficiency, I could enter in the BTP only the branches that are taken. I would not enter the target address of not taken branches into the BTP. This is considered that I have, for example, a branch that's executing a loop, and that branch is never taken. So I would be polluting the BTP with the target of that branch which is never used. And the other thing is that the address of the taken branches are added to the BTP at the back end when not only the outcome of the branch is known, but also we know that the branch will be executed and it's not speculative anymore. So the IBM PowerPC 620 had 2056 entries and two-way set associative BTP, which 2K counter PHT. So that illustrating that the size of the BTP and the size of the PHT in this design from IBM is different, and therefore they are decoupled. In this processor, there is also a one cycle penalty for branches that are predicted not taken and that have a BTP hit. The next question is if we should be integrating the BTP with the branch history table in the case that I have a global set predictor. Remember, global set predictor is one that has a single history, but that history can be indexing multiple PHTs. So this is the situation where I have multiple PhDs and I have a history. In this example, it's talking about a local history, but I could do the same design with a global history. Remember, the difference between a local history and a global history is the local history is looking only at the most recent the outcomes of the same branch, and the global history is looking at the outcome of branch that came before that. So in this design, again, I have some of the bits of the PC that are used as the tag in the BTB, and some other bits of the PC that are used to select which PHT are going to use, and also what is the entry in the BTB that I should access. Um, in this case, both taken and not taken branches must be in the BTB plus the branch history table because I need the history even if the branch is not taken. Um, so again, this is a cartoon design. Most likely, I'm not going to use the same bits to address or to index the branch target buffer and select the PHT. It's not likely that I have the same number of PHTs as I have entries in the BTB. So the Intel Pentium 6, the Intel P6, sorry, used this design, has a 4-bit local history, and it has 512 BTB entries. And the number of PhD that they use in that design was never published. One of the questions is what happens on a BTB miss? On a BTB miss, I'll have no history for the branch because I have integrated the history table with the BTB. So, and why would I have a BTB miss? One is that the first time that I execute in this branch, in this case, the history wouldn't have much information anyway. But the other situation is that the branch may have been evicted from the BTB because it has not been executed for a while. And when I evict the branch from the BTB, I also lose the history. So I can have situations where I have no history. In this case, the solution is to use a static prediction that if the branch is backward, it will be taken. If it's forward, it's not taken. But the predicted taken branches, we're going to have to wait for the target address computation in this case. So next, let's talk about indirect branches. In an indirect branch, the target of the branch is stored in a register. So consider that branch that I have here. This illustration is illustrating a series of instructions, and I'm focusing on that red line in the middle. That's the branch. So the first time that the branch is executed, it has the target indicating the figure. And in other executions of the branch, I have different targets, and the targets can repeat in execution of the branch. So I have a dynamic branch that where it changes the target, or it can change its target every time it's executed. So what happens in this case? In this case, I have to consider what we call misfetch. What is a misfetch? So if I have a branch that is correctly predicted as a taken branch, and there is a hit in BTB, but the target address that I got from the BTB is wrong. Why is that target address wrong? Because the branch is changing targets between executions, and I may have stored in the BTB the target from the last time that I execute the branch, which is different this time. So when this happens, I say that I have a misfetch in the BTB. So it is obviously caused by the indirect branches. Indirect branches happen more commonly in object-oriented languages. One strategy that I could use a hysteresis cycle, just that, like I use for the branch prediction, where I do not change the target of a branch whenever the branch target changes. So I do not change the entry in the BTB. I use a saturating counter. And I will only change the target of a branch if I see two misfetches of the same branch. So again, it's to avoid this situation where a branch most of the time go to one target and then sometimes only goes to a different target. This will be the similar to the misprediction of branches in the end of an inner loop that we studied before. So the Intel Pentium M has an indirect branch predictor, and it associates global history registers with the target address. There are two instances of mispredictions that we have to consider. One is that we mispredict the direction of a branch. So in this case, typically what we're going to happen is that the recovery only will occur when the branch is at the head of the reorder buffer. The consequence is that I have lots of instructions that will be nullified because of misprediction the direction. The other situation is that I do predict the direction of the branch correctly, but the BTB, I have a miss in the BTB, so I do not have the target. So in this case, I cannot fetch the instructions until the target is computed. But remember, the time to compute the target is shorter than the time to find out that the branch goes to the other directions. So in this case, it only affects the filling of the front end for the processor. So in RISC-V, the instruction that implements an indirect branch prediction is the JAL-R instruction. And remember, the JAL-R instruction the target of the JAL-R instruction will be given by the value in a register. This is the format for the JAL-R instruction, and what it does, it takes the value of PC plus 4 and put it in the destination registers. And in the PC, it takes the value of the source register 1 plus the value of an immediate. So as you can see, you have a computation to do based on the value of a register. And if the value in that register changes, the target of this branch changes as well. What are the limitations that I have of the tagged BTB if I have a polymorphic indirect branch? So remember, indirect branch, we say that a branch is monomorphic if the target is always the same. If the target can change when the branch is executed in different instances of execution, we say that's polymorphic. So what happens here is that if this branch is mapped to a BTB using as a index plus tag the address of the branch, this branch will always map to the same entry in the BTB. And as it changes targets, I'm not going to be able to, I am not able to store multiple targets of this branch. Even if I have a simple case where a branch only has 2 targets, I cannot use 2 separate entries in the BTB to store the multiple targets or even multiple entries of the BTB to store multiple targets of the same branch, because the indexing of the BTB and the tagging of the BTB is based only on the branch address. So in this case, all instances of the same branch must map to the same entry in the BTB. There has been several designs that improve on that, and we'll see that in the second part of this lecture.